So the last couple of days we've been talking about properties of light. Yeah. One other thing we need to talk about first before we can go over how light is actually produced, and that's the energy that light has. Now yesterday, remember, we talked about ionizing energy, and we looked at that chart, and we said that below ultraviolet,
not one thing, it's another.
Below ultraviolet, light doesn't have enough, those types of light, like radio waves and infrared and microwaves, don't have enough energy to ionize. Okay? The way we usually think about it is that energy is proportional to the frequency. Okay? So, I don't know if you guys have ever seen this sign before. This means not equal to, but proportional to. And basically that means the higher the frequency of the light, the more energy that it has. Okay? So gamma rays have the highest frequency of all the types of light. Radio waves have the lowest frequency. So gamma waves have the highest energy, radio waves have the lowest. As far as visible light is concerned, if we are only looking at visible light, blue light has the highest energy, and red light has the lowest. Okay? What? All of it? For light, blue light has the highest energy, and red light has the lowest. Because energy is proportional to frequency. Blue light has a higher frequency than red light does. Okay? So, thinking about our chart, what type of light would have more energy than visible light? Or what types? Gamma would, yes. X-rays? No, radio's got lower energy. UV. Yeah, all of UV. Okay. So if we look at visible light, ultraviolet and X-rays and gamma rays all have more energy than visible light. Nope, because it would block the UV, and yeah, that's true. So yeah, infrared goes through just fine. So heat. But what? It's in your picture packet. Equalize the pressure. Now, this right here is going to be very important to when we start talking about how light is produced. So we just want to remember, higher frequency equals higher energy, okay? Let's go by this. Yeah, you guys are going to have homework tomorrow for sure. So yesterday we were talking about emission spectra and absorbance spectra, right? And to kind of show you how that works, I've got these gas tubes. So this tube right here is filled with krypton. So if we look on the periodic table, krypton is number 36. It's a noble gas. Noble gases don't react with things, but if you send electricity through them, they still will glow, I guess. A lot of neon signs, are filled with noble gases because they glow different colors when you send electricity through them, but also because they don't react. You can get oxygen to glow when you send electricity through it, but oxygen also is very reactive, so it will react with other things in the tube. So, different gases will glow different ways. We tend to use noble gases in gas tubes just because they don't break down as easy. So, this right here generates an electrical current, high voltage electrical current, and so we're going to ground it. This is, I think I did this last year, maybe a little bit for you guys. This is our wonderful ghetto setup here. We're going to ground it through faucet, plug this in.
What happened if you grab the paper from
I don't think you'd feel enough current, but you can see it glows, you know, kind of a pinkish light. Okay? So let's compare that. Let's change the tube out. Let's put in, we've got a few different tubes here. We'll save neon for last. Let's put in carbon dioxide. So this isn't even an element, right? It's a compound made of carbon and oxygen, but it's still a gas. And so when we send electricity through it, I've got a few that I bought for this purpose. So I hate to keep bringing up CGB, but there we had this nice little thing that you just slid the tube in, and then you turned it on.
We're boring.
What happens if you break the tube?
The gas would escape. I mean, it won't work anymore because it has to be, you know, sealed off from the atmosphere so that the gases can't. That's true. Uh-oh.
Did you ever get in
Nope. There we go. So you see carbon dioxide is kind of a bluish color, bluish green a little bit. What? That looks like the same color to you? All right. Isaac is underwhelmed. Now, here I have helium. Here, this tube is made a little bit differently, so we have to be careful. They've got coatings here so that you can see the differences. We're just looking at the clear part here. So when I set this up, we're looking at the part that is closest to the actual faucet. Okay, the interactions with the coatings is going to be a little bit different situation. So you can see more of a brightish pink. So we're looking at this part right here, right? Yeah, but it's reacting with the coating. It happens to give off the same color in this case. You just want to be careful what we're looking at. Okay? And then, so that's helium. Here we have mercury. So mercury, if you decrease the pressure enough, mercury is usually a liquid at room temperature, but if you decrease the pressure enough, it will turn into a gas. It turns out that these types of lights up here actually have mercury vapor in them. So, yeah, if you break one, you should kind of get away and let it dissipate. So what we're going to see is the mercury, the color of the light that's given off by mercury right here, okay? What you'll see over here where the coating is a little more like what's going on with the lights, because the lights have a coating all the way around them. Now, here it's reacting in a way that gives a green color, but again, there's a coating on it. This part right here is where we're looking for the actual color of the light that's given off. Yeah, kind of a dull blue. And this right here would be more like what's given off by the light. It's just it's not as bright because of the way the setup is with the electricity. Okay. So that's mercury. Dank. And then here is neon. Yeah, there's no coating. The newer tubes that I bought, they don't have any coatings anywhere.
But they just have all the newer ones at CGB.
Yep. Uh-oh. Okay. So real neon lights are that color, right? Anything else that we call a neon light that's a different color, it's some other gas. So neon has kind of been the term that we've applied to those, but this is the actual color that neon gives off when it is electrified. Okay? So that's kind of cool. Braden, shut up. All right, here, these are spectroscopes. I don't have enough for everybody, so you kind of got to share betwixt yourselves. Yeah, you guys got one. Okay, now listen. Let me see this. Okay, here's how you use these. You look through this end, okay? Look through this end. What you want to do right now is just point them towards the lights and look through there, and you'll see kind of a rainbow of colors. And what this is doing is it's separating the white light into its colors just like a rainbow or like a prism. The light from the lights, what the spectroscope does is it splits it into its actual colors so that you're seeing the specific wavelengths. Your white paper is bouncing the light off, so yeah, you would expect to see basically the same colors.
Okay, what am I supposed to look for when I shine it up there? It just makes it brighter. Well, there's a rainbow,
yeah.
But I see that when I don't even look at light.
Well, that's because light's coming through it. It looks brightest when you look at the light.
Well, I see no rainbow.
What?
I'm serious. I don't see no rainbow.
Nothing now.
Oh, this one's broken.
Yeah.
Yeah, this one's messed up. Sorry.
So how do I tell what number it's supposed to be?
Here, take mine.
Well, these are obviously cheap. So that there are better ones that you can look through and you can perhaps and you can actually see the numbers that are on there. Now listen, the problem is the science teachers that you've had in there here the last few years, they haven't spent the money in to buy equipment and stuff. So I'm trying to rectify that. Okay. Now, what we want to look at is we want to turn on that neon tube again, and we want to look through there and see the wavelengths that are given off. Right. Now, from back there, it's probably not going to work so good. Oops, I stole this from somebody. Oh, no, that's the broken one, right. Okay, so we might have to just kind of form a parade to come by so that you can kind of stand here and look right at the tube and share the things down the line. Okay? We'll want to turn this off and this off, and hopefully that will be enough. Yes, I am. So if you don't want to move, that's fine. But if you would like, come up and you can look through the tube at the actual. Yeah, that's the broken one. Hopefully not. Can you see? Anything?
What? Maybe he's left-side dominant.
Yeah, I'm right-handed, but I'm left-side dominant.
Yeah, that's how I am. That is why I'm so important.
Here, let me see that quick.
No, I shoot gun right-handed, but I'm left-side dominant. Some favorite shot.
Okay. I don't know if I'm coordinated enough to do this.
When something's moving a certain way.
Yeah. So what you should see when you look through this is, hey, be quiet a minute. What you should see when you look through this, when I've got the thing electrified, is you should see some bright lines, but all those bright lines should be in like the red and orange parts of the spectrum. So look kind of towards the edge of the spectroscope. Obviously you need to point it at it, but.
I just see the number. Oh, there's the colors. I got it.
You see it?
Yeah,
see, so there's like
a 4 in the purple or something.
Okay. You don't really see any green light. Now, we'll try one more here. But here's the point. What we're looking for is an emission spectra. Okay? This looks mostly red to us because the colors that are given off are mostly in the red and orange part. Okay? If you look through there and you see the lines in the spectroscope, you should see some bright ones in the red and orange. There might be a faint one in the purple, but most of the wavelengths that are given off are in the red and orange. And that is going to be, again, specific to the neon. There shouldn't be any other element that gives off those exact spectral lines, those exact emission spectra. Okay, let's take a look at carbon dioxide. Same way, and we should see different lines that come out because this is a different substance. No, this is blue. Can you see those spectral lines? What do you see, Grace?
I
see,
and then put the little flash on the color. And then blend.
Oh, I see like rainbow.
Okay, what are the brightest colors in there?
A greenish probably.
Okay.
I think it's green.
Yeah, move your eye around a little bit so you can see them.
Yeah, probably like greenish fluid.
Okay.
What are you holding, Mr. Roark? Oh.
I wish it was brighter so you could see the numbers in there, but. Okay. What we need to do is explain what is actually going on. We're going to do so looking at hydrogen. Okay? So hydrogen is going to kind of be our model, and then we can expand that to other gases. When we look at hydrogen, this is the emission spectrum that we see. I don't have a hydrogen bulb, unfortunately, but there was one at CGB. But we didn't have neon at CGB, so you guys got that. All right. So when we look at hydrogen, if we were to have a hydrogen tube here and have a little bit better spectrometer that we could see the lines and measure them a little bit, what we would see is we'd see one line kind of in the red, we'd see another one right here, and another one right here, and another one right here, and another one right here. Okay? So hydrogen shows these different lines in the visible range when we look at the light that's produced running electricity through. Okay, so what do you mean a bunch of colors?
I don't know. The whole rainbow lit up when I looked at most stuff with that thing.
Well, yeah, so in some cases, what you're actually looking for is those specific wavelengths, okay? And because these are just cheap handheld ones, it's a little bit hard to tell, but a better spectrometer, you'd be able to see, oh, this wavelength is at exactly 440 nanometers. And by reading those, you can tell what elements are actually there. So we could actually have a mixture of hydrogen and carbon dioxide, and we would be able to see, oh, because this specific wavelength and this specific wavelength are there, that has to be hydrogen, and then the other ones that are in between there, that shows us that there's carbon dioxide. So you can have a whole mixture of gases and be able to, just by reading those spectral lines, figure out what gases are in that. okay? And like I talked about yesterday, if we have bright light, if we were to take a hydrogen gas and hold it up to a bright light and then look at it, we should see that those colors are subtracted. Those are missing in the total rainbow, okay? And that's just the difference between emission, where we're sending electricity through and producing light from the gas, and absorption, where light is going through the gas and we're seeing what comes out on the other side. So in an absorption spectra, we should see all the colors except those specific wavelengths, okay? So how do we explain where these lights come from and why they have these specific patterns? Oh, this shows what you should see. So here would be mercury, okay? Here would be helium. We did helium. There's the hydrogen one. Neon. You can see there's actually lots of different lines right there through the handheld spectrometers. It kind of looks like there's 2 or 3, but there's lots of little lines right there in the red region. And again, you could overlay all of these, and we can see, mercury has these 2 that show up that aren't in anything else. Hydrogen has these that show up that aren't really in anything else. So we could actually fingerprint those different elements. Light is produced when electrons fall from higher energy levels down to lower energy levels. When we send electricity through that neon tube, the electrons in the neon get bumped up to higher energy levels. When they fall back down, they give off light. So the electricity bumps them up. They're not going to stick around up there, though, in those higher energy levels. They'll fall back down, and they'll give off wavelengths of light. An analogy to this is to think about a stair step as your energy levels. Now, again, we're going to talk about hydrogen because it's the simplest element. How many electrons are in a hydrogen atom? This one. It's got 1 proton and 1 electron. So that electron, if we were to write the electron configuration for it, it would be in the first energy level, right? 1s1. So that electron kind of spends its time in the first energy level. If it gets enough energy, though, it can actually get bumped up to a higher energy level. So let's say it gets enough energy to get bumped up, to the next energy level up. And again, we can think of it kind of like stairs. Remember, energy levels, you can be on one energy level or you can be on another one. You can't be anywhere in between. So this hydrogen, or this electron right here, it has to get enough energy. If there's not enough energy going through there, it won't get bumped up. If there's enough energy, it can get bumped up to this energy level. It has to be the exact right amount, though. Okay? That electron, not when it's moving up. No. It has to be absorbing energy. But that electron won't stay up there. Electrons always like to fill in the lowest energy levels that they can. So they get bumped up, but kind of like if you take a basketball and you throw it up on top of a mound of dirt, you can get it up there, but it's not going to stay up there. It's going to come back down. Okay? Except instead of rolling back down, this electron is going to jump back down. When it jumps back down, it will give off energy. It will give off light. Okay? Now, if you notice, the way I've drawn this stair step, what happens to the stairs as you get higher and higher? Yeah. So as you go up in energy levels, the energy gaps get lower and lower. This is why we see different colors of light that are given off. Remember, energy has to do with frequency. Okay? When we go from this energy level down to this energy level, that's a big jump in energy, which means that's going to be a big I should say a lot of energy carried away by that light, which means it's going to have a high frequency. Okay? If we jump from this energy level to this energy level, that is a lower change of energy, and so a different wavelength of light will be given off. Okay? If an electron gets enough energy, say, to get knocked up to this energy level right here, there's actually a few different things that can happen. It could jump all the way back down. Okay? That would be a big jump of energy, which means a high frequency type of light will be given off. Or it could jump from here to here and then back down. So there would be two different wavelengths of light that are given off. It would give off a small frequency light right here and then a bigger frequency light right here. Or it could jump from here to here and then back down. Or it could jump from here to here and here to here and here to here. Every time it jumps, it's giving off light. The type of light that's given off depends on the change in energy. If it's a small change in energy, you get a low frequency of light, more towards the red end. If you get a big change in energy, that would be a higher frequency of light, more towards the blue end. Okay? The thing that can be a little bit confusing here, even though this is the biggest step in energy, this right here, jumping from this energy level to this energy level, is not actually going to give off blue light. This will be sort of an intermediate. For blue light to be given off, it's going to have to jump from a higher energy level all the way down. Okay? For red light to be given off, you're going to have a small change in energy. So it might jump from here to here. Okay? Anything in between would be some other type of light, like green light or something like that. Now, I'm just using those as examples. We'll kind of get into the more specifics in a minute. But the thing to realize is every time light is given off, there is a change in energy level. Every time there's a change in energy level, one type of light will be given off. And we can look at that. Okay? Does that make sense? So to use the stair-step analogy, it'd be like if Braden was standing at the bottom of the stairs, and we took him and we threw him, and because of how fast we threw him, how hard we threw him, how much energy we gave him, he landed on the 5th step. Okay? Braden doesn't like to be on the stairs. He's scared, so he's going to get back down. But how he gets back down, I mean, it really is completely random as far as electrons go. He could jump from the 5th stair to the 3rd stair, and then the 3rd stair to the 2nd, and then the 2nd all the way down. Okay? Each time he jumps from one step to the next, he would give off light, so he would glow with some wavelength. But the color of light that he glows with depends on how far apart the steps are that he's jumping in between.
So you could jump from the very top to all the bottom?
Sure, and that would give off a lot of, use a lot of energy, so that would be a high frequency of light. Like a bomb, not exactly. Okay? Now, if you have just one hydrogen atom and you were to electrocute it and look at the light that was produced, what you would see is that it would be flashing different colors all the time, okay? Because sometimes that electron would be kicked up and it would fall all the way back down. Sometimes it would fall down to the next one down and then the next one down and then the next one down. It's completely random how they come down. Well, the problem is a single atom is not going to give off enough light for us to see with our eyes. We'd have to be measuring it with some pretty sensitive machines. The reason why we don't see flashing different colors in a tube like this is because there's lots of atoms in here. And if we look at one atom, as the electron goes up and comes back down, it might do that big jump all the way back down. But the atom right next to it is going to do a different jump, and the atom right next to it is going to do a different jump. And so you have all these mixtures that are coming out, and that's why we see, kind of one color. It's the different wavelengths that are coming off. But what the spectroscope does is to break that apart. So this light here corresponds to one atom, or, a bunch of atoms doing one type of jump. This would correspond to a different jump. This would correspond to a different jump. Okay? This would be red light would be a fairly low level energy jump, so something where the energy levels are close together. The purplish light would be a bigger energy jump. And that's how all light is produced. Okay? If you heat up a piece of iron until it's glowing hot, okay, there are electrons in those iron atoms that are getting knocked up to higher energy levels and they fall back down. They give off light. Same thing is happening in here. In the sun, electrons are jumping around. Every time light is produced, you're getting some sort of electron jump. Yeah, let's go with this right now. I should erase this. We can actually calculate the change in energy that is associated with the type of light produced using this equation right here. Okay? E equals F times H. H is a constant. It's called Planck's constant. So that's what we have right here. Okay? Planck's constant is just a number. All constants are a specific number that helps us relate two measurements. And it is 6.63 times 10 to the negative 34th joules times seconds. Okay? Now the units there, I mean, we have to have units with stuff, but they aren't all that important to what's going on. The point is, this constant helps us relate the energy level jump between electrons to the type of light that is given off. Okay, so this is a pretty small number. F, of course, stands for frequency. What are our units going to be for frequency? Hertz. And E stands for energy. And the way we're going to think about it, the way it's related to what we're talking about, is this is basically the energy gap between electron energy levels. Okay, so if we look at a hydrogen atom and we look at the difference in energy from, say, the second energy level to the fifth energy level, we measure that difference in energy, we can put that in, divide by Planck's constant, and that will tell us the frequency of light that will be given off if an electron jumps from that energy level down. So if we know the energy level gaps, we can actually calculate what color of light will be given off, what type of light, simply using this equation. And we will do some practice problems with that coming up. Yeah, I did. Planck's constant. It's not an equation. How is it an equation? No, those are units. This isn't an equation. These are the units. Joules times seconds. No. No, these are the units. The reason why it's J times S is because the energy is going to be measured in joules, okay? And frequency is measured in times per second. So if we multiply this by times per second, the seconds cancel out and we get joules. The units for constants, all they are there for is to relate the measurements that we're using for the other things in the equation. No, you don't plug in numbers here and here. These are units. Okay? Let's see. We should probably do a practice problem. I think that'd be a good idea before we move on. Let's watch ghost videos. I'm going to say no. Okay, let's say we measure the energy level gap between two energy levels in an atom, and we find that it is 5.29 times 10 to the negative 19th joules. Okay, what we want to do is calculate and then figure out what type of light is going to be given off if we have an electron that makes this energy level gap, that jumps down from the higher energy level to the lower energy level over this gap. Okay, so the first thing you want to do is use the equation that we just got to calculate the frequency of light that's given off. And then we can compare that frequency to the chart that we had the other day to figure out what type of light it will be.
Oh, boy.
Is there like a chart for what kind of light it is?
No, you better just know.
Yeah, yes.
It's 0.03 light.
So you look back in your picture packet to when we talked about the different types of light. They have the frequencies that are listed there. Okay, this is another case where it might make sense to use your calculator because we have another constant that we can use. So instead of having to type that in all the time, you can store Planck's constant for h in your calculator. Remember, type in the number, use that arrow, and then store it as a letter. I would pick h because that would make sense. Remember, Planck's constant is 6.63 times 10 to the negative 34th. You understand what? Anything? So, this is just a three-step equation. A 7. Where is this? There's no 7 up here. 34th.
I got an answer, but it looks awful big.
Yeah, how do you set the h?
Type in the number. So first type in 6.63 times 10 to the negative 34th. And guys, I see a lot of people using the wrong e on their calculator. Don't use the lowercase e. That's the natural number. Use the double e. On these Inspires, it's... Where is the double E? Yeah, it's right next to the A on the bottom. That is the thing that you should be using for this right here.
Roark, is it supposed to be this big? 7.97888 times 10 to the 14th?
Yep.
Wow, I'm a genius. I did that in my head.
So now we want to go, what kind of light is that?
No, I mean...
Oh, there. Then hit the arrow, the store. On these, it is... Let's see.
To do what?
To store it. Yeah, where's the store? Oh, yeah. It's the blue thing. Yeah, Control VAR. So
Control bar.
var. It's above the var thing. And then pick your letter.
It sounds more science.
Okay, hit enter. So now you have stored that as H. So now you can just take...
Yama.
Open.
Yama. Oh, my God. Because I don't need...
Yeah. Okay, listen, if you're having trouble with your calculators, you're going to have to come. I can help you, but, I've already taught you guys how to do this. If you don't remember, sorry. We'll review it, but not during class, okay? So, to calculate this, we put this in for the energy, and then to find the frequency, we have to divide by Planck's constant, and we get 7. Isaac, for the love of God. As I was saying, what we have to do with this then is figure out what type of light this is going to be. If we have light with a frequency of 7.98 times 10 to the 14th hertz, what type of light is that going to be? Let's go back to our chart.
Are we going to have to memorize that chart?
No.
Wait, this is
Oops.
the number you got?
Okay, this thing right here. I
No,
understand this is the best I got for you right now. So, we see, right, we want to look here on the frequency. And, I mean, I know it's 7.98, but these are, you know, just going to be kind of in between. So it's going to be about right in here, the 10 to the 14th. So that's going to be infrared light. Okay? So I would expect to see a problem much like that on a test where I say, here is the energy jump between energy levels. If an electron falls, you know, from the higher energy level to the lower energy level, what type of light will be produced? So you have to use that equation with Planck's constant to calculate the frequency, and then you'll have to be able to go to a chart that will show what type of light that's going to be, and read it to figure out whether it's infrared or visible light or whatever. Can I go back to how I got that? Yes. Again, it's just a three-part equation. Okay, this is the energy, right? That's what was given to us. And Planck's constant doesn't change. It's always this. So we have this and we have this. We need to find the frequency. We divide by Planck's constant on each side to find that frequency. Oh, good. Oh, and I sort of forgot. You actually have a chart in your packet, at the beginning of your packet, where all the constants and stuff are, that, you know, shows it a little bit bigger. So right there, you have that to see what types of wavelengths would be produced. Now, the way this works is they've taken the visible light and expanded it up here so you can see it a little bit closer. Okay, the actual wavelengths there, but you would just want to read the frequencies down here to see kind of what range it's in. All right, so just to reiterate, here's what we got going on, okay? Here we have an electron that falls from this energy level all the way down to this one. That would correspond to high energy light, so it would be more up here in the purple end. Here we have an electron that falls from the third to the second. That is a lower change in energy, so that would correspond to more of a reddish color. Okay? Because we would have a mixture of hydrogen atoms, and each one is going to be doing something, you'd have one that might be giving off this purple light, one that's giving off this, one that's giving off this. Okay? And so each of those energy level changes is happening in different atoms, so we get a mixture of light that comes out. And, you know, we see it as a mixture, a certain color based on how those colors stimulate the cones in our eyes. Okay, but a specific spectrometer would be able to read those and give you those exact wavelengths. So it's all about energy level jumps. Now, this also explains why we get absorbance spectrums, too. If you shine white light through a tube, then those wavelengths of light are going to interact with the electrons, and they'll knock them up to energy levels. Okay? And when a light wave gets absorbed by an electron, it disappears. So when we shine white light through here, we see those same gaps, except taken out, because the electrons in there are absorbing those electrons as they jump to higher energy levels, and they're getting subtracted from the white light that's coming through. And that's why we see the absorbance spectrums being lined up with the emission spectrum. I didn't say you were talking. It's just like, you're like, oh, it's almost time to go. I better put my stuff away. Yeah, you don't think you might need that pen a little bit longer here? Oh, my. So, that's the basics of how light is produced. Tomorrow, we're not watching ghost videos. Tomorrow, we're going to talk a little bit more about how light is produced. We're going to get ready for the lab. We were going to have lab tomorrow, but we're going to need a little bit more time to get to prepare for that. But I will... I will not be here on Friday, though, so you guys are going to have to do the lab on your own. The lab will involve Bunsen burners.
Oh God, that was our fault.
Really think
That was our fault.
Well, it's either that or we skip the lab altogether.
Who's gonna turn on the gas for us, though?
Well, I'll have Miss Erickson do that. She knows how.
there's not even gonna be a sub.
Yes, there's going to be a sub, but the sub is not going to know anything about doing flame tests. So, we will talk about it a little bit tomorrow. We'll talk about Bunsen burner safety tomorrow. But as far as the actual lab goes, you guys are going to have to be prepared and know what you were doing when you come into class on Friday. Okay? Can't understand why anybody would hate you.
I wasn't even that bad today, Mr. Roark. I was asking questions. I was being involved.
I have one problem. I'm like, am I supposed to go like write more down? Because I would. And I'll redo the assignment, I suppose.
You can never give me your answer.
Here's your question of the day.
Is that an 18?
That is a negative 18, yes.
Oh, wait, so don't
Good.
We're gonna do her. You wanna look at the chart?
Your homework for tomorrow is to do, what is the next worksheet? Yeah, 3.4. Please realize 3.4 has two sides. We've had 2 nights without homework. We're catching up.
It has a wavelength. These are the it says wavelength.
Yeah, negative 18.
It only goes down to 7. Negative.
That's what I am looking at.
Oh yeah, it does only go that far. You'd have to actually do the calculation then.
Oh my God.
How do you do that?
You did-
Oh, bro.
Might have 2 that don't work now. It's fine. Sort of. Mostly.
How do we solve this? Because this isn't what we just did, was it?
No, it isn't. It's the other equation.
One thing has an arrow.
Other equation?
Hmm?
Oh.
I can't see what that is, though.
The C equals wavelength. I mean, we did problems like that the other day. Speed of light equals wavelength times frequency. C equals F times lambda. I don't know.
Yeah, I wrote it down here.